Lesson 3, Newton's Law of Motion, pages 24 to 33. All right, as always, we're going to start with the connect it. So a hockey player hits a puck that was at rest on the ice. We need to mark an X on the point in the image where the hockey player first applied a net force to the puck. All right, and that's going to be at the base of the hockey stick. So that's where it hit. So how did the motion of the puck change as a result of being hit and the puck accelerated from being at rest? After being hit, the puck travels along the ice at a constant speed. What might cause its motion to change? And the puck could experience a net force such as a hit from another player or contact with the net of the goal. That would cause a change in motion. So just to read the caption, speeding up, figure 1. Just a moment ago, the puck was at rest on the ice. The net force that the player applied to the puck caused the puck to accelerate. So that there is what told us that he hit the puck with a stick. Newton's first law of motion. Okay, so that is that an object's motion will not change unless a non-zero force is exerted on it. So an object at rest will remain at rest until acted upon it by an outside force. And an object in motion, moving at a constant velocity, will remain in motion unless acted upon by an outside force. Some different examples, as we just saw in the connect it, a hockey puck sitting still will remain at rest unless a player hits it, applying a net force. A hockey puck slides in a straight line across the ice and the motion remains constant until it hits something like the goal or another hockey stick. Voyager 1 spacecraft launched in 1977. It is still moving through space at a constant velocity with no means of propulsion. Inertia. Inertia is a resistance to change in motion. Newton's first law is also called the law of inertia. When a car stops suddenly, why do the passengers keep moving forward? And that's because of inertia. How does inertia relate to the use of a seatbelt? So seatbelts allow us or keep us from doing what this lovely lady in the image happens to her and flying through the windshield. So if we stop too soon, we're not prepared for it. Whatever is the case, if we didn't have a seatbelt, it wouldn't stop us from flying out, as is happening with the motorcycle. He hits, he flies off. Inertia and mass. So which object, you or the car, is harder to stop? Oh, the car is going to be harder to stop because it's bigger. So the greater an object's mass, the greater its inertia. So suppose each of these women wants to move the dog off her lap. Which dog has less inertia? That, of course, is going to be the small one. And which dog is harder to move? That, of course, is the large one. Now, the reading check. How does mass relate to inertia? The greater an object's mass, the greater its inertia. Newton's second law of motion. An object's mass directly affects how much force is needed to accelerate the object. Imagine pushing a shopping cart. What are 2 ways to cause the cart to speed up? So we can either apply a greater force and push it faster, or again, you could just push it and leave it. That would make it go faster also. Increasing force increases acceleration. Increasing mass decreases acceleration. So with this, the philosophy is that we can increase it by increasing force, or we can increase it by taking stuff out of it or decreasing mass. Newton's second law of motion. It can be written as a mathematical equation. The size and direction of a net force equals the mass times acceleration. So F equals ma. Net force equals mass times acceleration. This equation can be rearranged to solve for acceleration, where acceleration equals the net force over mass. Newton's second law: the force applied by these two horses pulls the sleigh and the people it contains. This sleigh can contain up to 12 people. How might you change the number of people to increase the sleigh's interaction? Fewer people would increase the sleigh's acceleration. And how might you change the number of people to decrease the sleigh's acceleration? More people in the sleigh would decrease the acceleration. So then answering those questions, what is the relationship between force and acceleration? As force increases, acceleration increases. And the relationship between mass and acceleration is that as mass increases, acceleration decreases. Calculations with Newton's second law. Net force equals mass times acceleration. So we have another triangle here, force at the top, mass bottom left, acceleration bottom right. So force is measured in newtons, abbreviated with a capital N. Mass is measured in kilograms, abbreviated kg. And acceleration is measured in meters per second, every second, abbreviated meters per second squared. You can use the triangle to rearrange the equation to solve for F, M, or A. So this is just like our speed triangle, just like density prior in the year that we've done, where you cover up what you're looking for and then that shows you. So if you're looking for acceleration, it's net force over mass. If you're looking for mass, it's force over acceleration. If you're looking for force, it's mass times acceleration. Reading check. Based on what you've learned, derive another equation for Newton's second law that is written to solve for mass. And you could use any of the ones that you could use the one wow, words are really hard. You would use the one that I just said there. Mass equals force over acceleration. All right. Using Newton's second law. So use the equations for Newton's second law to understand how mass and force affect the motion of a volleyball. Show your calculations for each problem. A volleyball is hit and experiences a net force of 2 newtons, which causes it to accelerate at 8 meters per second squared. What is the mass of the volleyball? So we have force and we have acceleration. We want mass. So mass equals force over acceleration. So mass equals 2 over 8. And that equals 0.25, so 0.25 kilograms. The same ball is hit again and experiences a net force of 3.5 newtons instead. What is the acceleration of the volleyball? And so for this, we have force and we have mass now. So we can find acceleration by doing the 3.5 newtons or force over the 0.25 kilograms of mass, which is equal to 14 meters per second squared. The same ball rolls horizontally along the sand and decelerates at a rate of 6 meters per second squared. Accelerate the force of friction that caused the deceleration. So for that one, we're going to do F equals mass times acceleration, so 0.25 mass times the 6 meters per second squared of acceleration, and that equals 1.5 newtons, which is the force of the friction. Newton's third law of motion. So for every action, there is an equal in strength and opposite in direction reaction. If one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first object. Force works in pairs, an action and a reaction. When you ride a skateboard, you move along because the ground provides a reaction force to the action force of your foot. Draw arrows to show the action and reaction forces between the dog and his leash and the gymnast on the beam. So we're going to do the dog and the leash. We have equal sides going in opposite directions for the dog, equal sides going up and down for the forces for the gymnast. After we're done with that, we should draw an example of action-reaction forces in the space provided, and you need to come up with your own version, and you will do this independently. So this is part of your workbook grade. All right, Newton's third law of motion. Balanced forces are different than action-reaction forces. Balanced forces are equal forces acting in opposite directions on the same object. These forces balance each other and produce no change in motion. Action-reaction forces are not balanced because they act on different objects. A motion example. A hockey player hits a puck. Action is the force of stick on puck. Reaction is force of puck on the stick. The puck has a much smaller mass than the player and his stick, so you see the puck accelerate. Reading check. A dog walks along the ground. If the dog applies an action force on the ground, what is the reaction force? And the equal but opposite force the ground applies on the dog is the reaction force. All right, here we have figure 5, understanding action-reaction. Action-reaction forces are applied to different objects. The action and reaction forces acting on a soccer player, a soccer ball, and the ground are shown with arrows. Finish labeling the forces to describe how they are being applied. All right, so down here on the foot, we have an action force, the player and the ground. The reaction force is the ground and the player. So with the ball and the foot, with the reaction force, we have the ball, which is applied to the player. The action force is applied by the player and applied to the soccer ball. Newton's laws together. So question it. Kirsten has a parakeet that likes to sit on a swing. Sometimes the bird makes the swing move back and forth. You want to investigate the bird and his swing and how they relate to Newton's laws of motion. List at least 2 questions you might ask. If the bird sits still on the swing, what forces do the bird and the swing apply to each other? How might action-reaction forces cause the swing and the bird to move? All right. Figure 6. So for each description below, decide which of Newton's laws is being described. The riders exerted on an action force on the safety bar. The bar exerts the same amount of force in the opposite direction of the riders. So that would be the third law. When the ride starts spinning, inertia pushes the riders back in their seat. That would be Newton's first law. And as the riders accelerate from rest to reach the same speed, riders with greater mass experience greater force. That would be the second law, Newton's second law. So in each space, provide or give an example in a way that one of Newton's laws is shown in the amusement park. And we just went over that. First law, second law, third law. Okay, there it is written out for you. So now it's time for our lesson check. So in your own words, what is Newton's second law of motion? An example, the net force acting on an object equals the product of the object's mass and its acceleration. What is inertia? Use an example in your description. An example would be your body continues forward when you ride in a car and it stops. This is because your body has a tendency to stay in motion because of inertia. What is the difference between balanced forces and action-reaction forces? Balanced forces act on the same object, and action-reaction forces act on different objects. You push on a door and it opens. Explain what happens in terms of action-reaction forces. So you push on the door, an action force, and the door applies an equal and opposite force on you, reaction force. You are stronger than the door, so the forces are not balanced. In question 5, a 12 Newton net force acts on a 4 kilogram jug of water. What is the resulting acceleration of the jug? Show your calculations. So force equals mass times acceleration, so 12 newtons equals 4 kilograms times acceleration, and acceleration equals 12 newtons divided by 4 kilograms, which is equal to 3 meters per second squared. And that is the end of this lesson.